Hi everyone, welcome back to ChemHelp ASAP. Today we are going to be using our delta H, our enthalpy of reaction, to actually do some calculations. Let's get started. So the most common thing that we use our enthalpy of reaction, or our delta H of reaction, for is to calculate the heat released or absorbed from a reaction. So let's start with a really simple example here. Given the following information, how much heat is released for 1 mole of each species? So we're given a reaction and we're given an enthalpy of reaction. And what I want to know is how much heat is released if I have 1 mole of my methanol, my CH3OH, 1 mole of my O2, 1 mole of my water, and 1 mole of my carbon dioxide. So let's calculate this for all 4 of our species for this reaction. Let's start with our methanol, our CH3OH. So to calculate how much heat is released for 1 mole of methanol, we're going to take our mole of methanol and we're going to multiply it by our delta H of reaction. So here is our delta H of reaction for methanol. You'll notice there is a 2 in the denominator. Why is there a 2 in the denominator? That 2 comes from the stoichiometric coefficient right in front of the methanol in the balanced chemical equation. Just yet another reason to make sure all of your chemical equations are balanced. And this gives us negative 726.5 kilojoules. Let's do the same thing for our other reactant. Let's do the same thing for oxygen. Again, we want to know how much heat is released for 1 mole of oxygen. So here's our 1 mole of oxygen multiplied by our delta H. Here is our delta H. Again, notice that this is per 3 moles of oxygen. Why? Because there is a 3 here in front of the oxygen in our balanced chemical equation. That gives us negative 484.3 kilojoules. On to our products. Let's do it for water here. Again, we want to find out for 1 mole. Here is my delta H. It's per 4 moles of water because there is a 4 right here. And this gives me negative 363.3 kilojoules. And for CO2, you know where this is going. Starting with my 1 mole of CO2, here is my delta H for CO2. Again, it's divided by 2 because there's a 2 right here. And this gives us negative 726.5 kilojoules. So when you have a heat of reaction, and very often it's reported like this, just kilojoules per mole, remember that this per mole is going to change for each species depending on the stoichiometric coefficients in front of each species. So let's work some examples that are a little bit more difficult than just having 1 mole of all species. Okay, so this problem reads, given the following information, how much heat is released when 35.4 grams of water is formed? We are given our balanced chemical equation again, and again, our heat of reaction here. Yes, this is the same equation that we just saw in the previous slide. But instead of having 1 mole of water, we are given the number of grams of water. So our first step is just going to be converting grams to moles. So starting with our 35.4 grams of water, here is my molar mass of water, converting grams to moles. Then using my heat of reaction, remembering that heat of reaction is divided by 4 moles of water because it has a 4 right here. That gives us negative 2.86 times 10 to the 3rd kilojoules. Our next problem reads, how much heat is released when 17.2 milliliters of methanol is formed? And again, they give us the density of methanol as 0.792 grams per milliliter. So just like in the previous problem, we've got to get to moles first. Now this is going to take us a little more work than just the molar mass because we are starting with a volume and we need to use a density. So here's my 17.2 milliliters of methanol. Using my density, I am going to convert this into grams. Once I'm in grams, now I can use my molar mass to convert to moles. And finally, using my heat of reaction, which has 2 moles of methanol, again, based on our balanced chemical equation, I get negative 309 kilojoules. Let's see a couple more problems given different initial conditions. So still using my same reaction. In this case, I want to know how much heat is evolved when 750 milliliters of a 1.35 molar methanol solution reacts. Again, the goal here is to get to moles, but this is going to take a little bit different process from the other problems we've seen. Starting with my milliliters of methanol, I am first going to convert those milliliters to liters. Then I'm going to use my concentration to get to moles of methanol. Once I'm in moles, I can use my heat of reaction, and I get negative 735 kilojoules. One last scenario to show you. I still want to know how much heat is released, but this time I'm starting with 0.985 liters of carbon dioxide at 1.18 atmospheres and 45 degrees Celsius. How am I going to get to moles with this information? I'm going to use ideal gas law. So ideal gas law, of course, is PV equals nRT. Plugging in my pressure, my volume, my value for R, and of course my temperature converted into Kelvin. I don't keep it in Celsius, it does go to Kelvin. All of my units cancel except for moles, and my number of moles is 0.04454 moles of carbon dioxide. Now that I have moles, I can use my heat of reaction. Again, it's divided by 2 moles of carbon dioxide because that is the stoichiometric coefficient, and I get negative 32.3 kilojoules. So there are lots of different ways that you can get to moles of whatever compound you're talking about. So you need to be flexible in terms of using your heat of reaction. The first thing that I think is helpful to think about is, how do I get the information that is given to me into moles? I hope you found this video helpful, and thanks so much for watching.